Hey everybody. Um, Looks like it's time to move on to section X.3, which let's not get into too much detail about why it's like X.3 and not X.2 or something. Uh, it's not really that important, but I'll just say I'm probably going off of like an old textbook and therefore like my old notes that I've just had for, you know, a handful of years now. But don't worry, I mean, it's just whether it's X.3 or X.2, just like the next section that we're doing here with matrices. And if you recall, X.1, we were using matrices to solve systems of equations. Like we would take, three or more equations and we would write an augmented matrix, right? And, that matrix had a line, like a vertical line in the matrix that was sort of like supposed to separate the left side of the equations from the right side. It was basically where the equal sign was, so that was like an augmented matrix. But normal matrices don't really have that line. So this is like a normal matrix. It's just an array of rows and columns. So just kind of so there's a more typical normal looking matrix, and I guess we're going to be dealing with those in section X.3 here as we look at matrix operations and just other random things about matrices. So the first thing I want to talk about is the order of a matrix, or the shape of a matrix. So the order, which is actually a pretty official term, the order again is really just the shape, and to specify that, we just look at the number of rows and the number of columns. So there are 2 rows in this matrix and 3 columns. So we describe the order as a 2 by 3. So number of rows, number of columns, makes you think of like a rectangle that's like a 5-inch by 8-inch rectangle or something, 5 by 8, or like a 2 by 4 piece of lumber kind of thing, like an area from geometry sort of feel. But this is just like the number of rows by the number of columns. This is a 2 by 3 matrix. So over here, this matrix, 7, -3, 4, and 6 right there, what would be the order of this matrix? Well, since there's 2 rows and then 2 columns, this would be a 2 by 2 matrix. Okay? And something else here, like what if I wanted to specify specific elements? And there's another actual vocabulary word, official terminology, element. So every single one of these individual numbers in a matrix, those are elements. And if I wanted to sort of specify one of them or refer to one of them, first of all, let me say that you can denote the entire matrix using like this capital letter A, and then you could also use capital B. So this is like matrix A, and we can call this matrix B. So over here, the entire matrix is matrix A. To denote just one of these individual numbers, one of these individual elements, I would use lowercase a, and then like 2, 1 in the subscripts. Now that might look like A sub 21 on the surface, but what this kind of says is like A sub 2, 1, where it's the element in, ready, row 2, column 1. So row 2, column 1. So row 2 is right here. Column 1 is right here. So in the row 2, column 1 position is that 2. Okay? So if I wanted A sub 1, 3, that would be row 1, column 3. So where is that? Row 1, column 3, looks like the 0. And, let's say I wanted to do, A sub 3, 3, row 3, column 3. Well, as it happens, there is no row 3. So looking for this, it's, not possible, or it doesn't really apply. So there is no A sub 3, 3 element. Over here, A sub 1, 1, where would that be over? Oh, no, I tell a lie. What did I do wrong here? If this was matrix B, then I should be using little b for the elements. So, that was a little embarrassing. So, B sub 1, 1, where's that? Remember, that's row 1, column 1, so that would be the 7. And then if I wanted to do, B sub 1, 2, again, where's that? Row 1, column 2, that of course would be the negative 3. Okay, so that's the first couple of just in these like very general matrix teaching points, right? The order, so the order of a matrix, and then how to specify individual elements. The next thing I want to talk about really quick is the very simple concept of matrix equality. It's just two matrices being equal to each other. And this is going to be pretty much exactly what you expect. So for two matrices to be exactly equal or equivalent, or whatever the proper word is, they have to, of course, be the same order. And, they have to have all the same corresponding elements. So in other words, it's a very long way of saying that the two matrices have to be exactly the same in every way. Same shape, same order, all the corresponding, everything matches. It's the exact same matrix. That's, of course, what two matrices being equal would mean. So if I were to contrive an example, is that a proper word in verb form? Contrive. If I were to contrive just some cheap example to kind of address matrix equality, maybe something like this, which you will probably see on your homework. I don't know. So let's say this weird matrix was going to be equal to, so of course that would be a 7. That's got to be a 1, and that's got to be a negative 3. Okay. So the question might say, what would be the values of x, y, and z that would make these two matrices actually equal to each other? So like, look, obviously the 7 corresponds with the 7, they match, so we're still in business. The negative 3 and the negative 3 obviously have to match, and then the 1 and the 1. But the 2x has to match what? 2x has to basically be equal to 6. So I don't know if you actually need to write this out like this, but you could set 2x equal to 6, and then, so 2x equal to 6, and then you could, literally solve for x and get x by itself by like dividing both sides by 2. And so, wouldn't you know it, x actually equals 3, so x has to be the value of 3. The y, to figure out y, well, we got this y plus 1, which has to equal the 10. So again, I don't know if you actually need to write this out or not, but y plus 1 equals 10. If you subtract 1 from both sides, it looks like y equals 9. And then the 4z must basically be -4. So again, you could write it out just to be thorough and safe and everything. And then if you get z by itself, it turns out that z has to equal -1. Okay? And that's another simple concept of matrix equality. Two matrices being equal, it's exactly, they're equal. Two matrices are equal, they're equivalent, they're the same matrix. And then you could do problems like that. The next quick thing I do believe might be adding matrices together. So I'm just going to write adding matrices. You'll see in a minute or two that subtracting matrices goes right along with this, because what's been true for many moons now, like all the way back to elementary school, maybe at least middle school, subtracting is adding. Adding and subtracting are essentially the same thing. But anyway, I don't want to go too deep into that. Let's adding matrices. So let's say that matrix A was like this. 1, 0, -4, and then I don't know, maybe a 3 and a -1, and then maybe a 6. So that would be what would be the order of this? So that's a 3 by 2, because there's 3 rows and 2 columns. And let's say that matrix B was this: 2, 5, -1, and then 0, and then maybe we'll toss a 4 in there for good measure, and then maybe a 19. Whoa. So this is also a 3 by 2, and when we think about adding matrices together, once again, it's going to be exactly what you would expect it is, okay? And that, the matrices must have the same order. Okay? They got to have the same shape. They got to be the same type of matrix, the same order of matrix. Otherwise we can't even add them together or subtract them together. That makes sense, because when we actually do matrix A plus matrix B, and again, we could literally write out this whole matrix and then a plus sign, and then we could do that, or we could just say, this I'm calling matrix A, this I'm calling matrix B, and then just write, shorthand, A plus B. You know what I'm saying? So you don't need to keep writing the full matrix, I guess, if we can just call it A and B. Anyway, this is going to play out, like I said a couple times now, exactly how you would expect. We're just going to combine the corresponding elements, and you could write a note for that, just kind of add the corresponding elements. Okay, I feel like I could make some sort of lame joke right now about The Fifth Element, which is a movie from when I was in high school or college that I watched numerous times in the theater. Pretty good movie, I guess. But you've probably never seen it, losers. But anyway, so we add the corresponding elements. And so that would mean that we do, right? So that would mean the answer matrix is just going to be also a 3 by 2. And we do 1 plus 2, the corresponding locations, the corresponding elements, like A sub 1, 1 and B sub 1, 1. Those get added together, and so there's a 3. So likewise, we're going to do the 3 plus that 0 to get 3, and then that 0 plus that 5 to be 5, and then that -1 plus 4, another 3, and then -4 plus -1. Remember, keep track of your simple arithmetic and negatives and stuff. -4 plus -1, I do believe, is -5. And then 6 plus 19, oh God, is 25. And so that's A plus B, Likewise, we could do A minus B, which again, like I said a few minutes ago, subtraction is really addition. Like you could just basically, I think I'm getting a little ahead of myself here, but you could, well, let me circle back to this. I might have done things a little out of order, but it's totally okay. Let's just literally subtract, so we're subtracting the corresponding elements. So the 1, it'll be 1 minus 2. So 1 minus 2 is -1. 3 minus 0 is 3. 0 minus 5 should be -5. -1 minus that 4 would be -5, correct? -1 minus 4. And then we have like the -4 minus a -1. -4 minus a -1. That's like adding 1 to -4. So that should be a -3, correct me if I'm wrong. And then 6 minus 19, I do believe, should be -13. There's also, it doesn't really matter. I think I meant to do this before the adding matrices part, but whatever. Gosh, am I going to spell? Oh my God, multiply. Holy moly. My brain just short-circuited there. So scalar multiplication. What this means is a scalar is a very fancy word that only applies in like certain situations. Matrices is one of them. So I can only think of one other one right now, but whatever. So scalar multiplication. A scalar is really just a number. Okay? So all we're doing here is we're multiplying, oh my God, a matrix by a number. Okay? So I'm just going to use the same, matrix A and matrix B from up here. So if I wanted to do, let's say, an example of like 2A, that's 2, and so 2 is the scalar. 2 is just some number, and we're doing 2 times A. So once again, good news. This is going to play out exactly as you would probably guess that it would. Multiplying an entire matrix A by just some number or scalar of 2, all that means is we're going to be multiplying every number, every element in matrix A by 2. It's kind of like the distributive property. It's technically not, but I mean, like, it basically is. Like, it acts the same way. We're going to multiply every element in matrix A by 2. So the 1 gets multiplied by 2, bam. The 3 gets multiplied by 2, ba-bam. 0 times 2 is still 0. Negative 1 times 2 is now negative 2. Negative 4 times 2, I believe, is negative 8. 6 times 2 should be 12. Okay? So, or if I wanted to do like negative 4 times b, right? So negative 4 times every number. So negative 4 is my scalar. And matrix B is all this 3 by 2 stuff up here. So multiplying everything by negative 4. So negative 4 times 2 is negative 8. Negative 4 times 0 is still 0. Negative 4 times 5 should be negative 20. Negative 4 times 4 should be negative 16. Negative 4 times negative 1 is positive 4. And negative 4 times 19, that should be like negative 76, I believe. Let's just go with it. Full send. Negative 76, because 4 times 8 is 80. Yeah, let's just go with it. So negative 76. Okay? And so that's how easy it is, scalar multiplication. So if I wanted to do a little grand finale here. So if I wanted to do like 4a plus 2b, and I wanted you to figure out like what that final matrix would be, you know, looks pretty simple. Like, you know, it's not that crazy. You could probably do it right now without even me helping you. So I would probably, reminder, like that's matrix A, 1, 3, 0, negative 1. So I'm going to write down 4a, like let's multiply matrix A by 4. So that would be 412. And then multiplying by 4 would be 0, negative 4. And then to keep multiplying by 4 would be negative 1624, I believe. And I hope I'm not making any silly mistakes. And then 2b, so 2b would be 4, 0, 10, 8. 4, 0, 10, 8. And then to finish, that would be negative 1 times 2 is negative 2, and then 38. So that's 4a, and that's 2b, and now we have to add them together. And obviously these needed to be the same order, but so my final answer, once again, I'm going to add the corresponding elements. So 4 plus 4 is 8, 12 plus 0 is 12, 0 plus 10 is 10, negative 4 plus 8 should be positive 4, negative 16 plus negative 2 should be negative 18, and then 24 plus 38, that should be 62, I believe. Let's go with it. Okay, so yeah, multiplying by scalars is just multiplying a whole matrix by just some number, and that's scalar multiplication. And then, you know, adding or subtracting or doing like these you know, matrix operations right here, where multiplying by a scalar and then adding the matrices, examples like this. So matrix subtraction, you know, like I was going to say earlier, you know, subtraction really is the same as addition. Like you could think of this as A plus negative 1 times B. So if you were so inclined, I mean, I wouldn't do this way, but you could like first multiply matrix B by a scalar of negative 1, and then just add the matrices, but whatever. You know, it's just a quick follow-up on what I said earlier, that subtraction is addition. I think there's only one thing left to do, and it is see, I know how to spell multiplication. Seriously, I'm not kidding. Like my brain, like I almost like blacked out for a second. So when I said my brain just like sort of short-circuited, I wasn't really exaggerating. Matrix multiplication. Okay, taking a breath here, right? Because I wanna make something clear before we actually get into this. Okay, matrix multiplication. All the stuff preceding this, like when we did scalar multiplication and adding two matrices together and stuff like that, I said that it was like exactly as you would expect. You know, it played out exactly as you probably would have guessed it would play out. This, not so much. This is going to blow your mind, okay? Like when I said, let's multiply two matrices together, and I said, how do you think that's going to play out? You'd be wrong, okay? Multiply two matrices together. You know, and I get it, like all this stuff is probably very new to you. I'd be a little surprised if I guess you've ever really learned about matrices before. But I definitely wanted to kind of go over some things with you because, you know, it is like a mathematical topic, and it's not exactly, I don't know, like there's a decent chance you take some math classes in college, matrices are going to come up, you know, like there. I think I actually took a math class called like matrix algebra or like linear algebra or something that involved a lot of matrices. So, you know, I definitely wanted to go over this with you, even if it was something you've never seen before. But, you know, anyway, to get back to my point, even if you, I know I keep on like beating a dead horse here, but if you had never learned about matrices before, you probably would have guessed how to add matrices and multiply a matrix by a scalar. But this topic, no. You would probably not guess how we do this. This is not what you probably think it is going to be. Okay, so let's do an example. Hope I actually explained this properly. So let's say we have matrix A, and let's start really simple. Let's have 5, and then 1, and then 2, and then 0. So this is a 2 by 2 matrix. And let's have B also be a 2 by 2 matrix. So let's say this is -1, and let's say this is 4, and let's say this is 1, and let's say this is -2. Okay? So we have a couple 2 by 2 matrices. Now, a little bit of foreshadowing. These are matrices that have the same order. They're both 2 by 2s. But to multiply two matrices together, they actually don't have to have the same order. Don't necessarily have to have, the same order. Whew! I told you, this is not going to play out as you expect. But these do have the same order, and we're fine, okay? They can have the same order, and that's great, but they also don't have to have the same order necessarily. So here's how this is going to play out. Oh my gosh, I'm so excited. To multiply two matrices together, so I'm going to do matrix A times matrix B. What you do is you multiply rows, entire rows, times entire columns. Let me say that again. We're going to multiply the rows of matrix A by the columns of matrix B. Okay? So, I almost want to get a pencil or like a different color here. So, row 1, okay, times column 1. Row 1 times column 1, and that is going to get me the like the row 1 column 1 spot, which is like right here, you know. This whole row 1 times this whole column 1 to just get that spot, that one final answer for the row 1 column 1 spot in the final matrix of like AB. Okay? So here's how this works. We're going to do 5 times negative 1 plus 1 times 1. So the first number in this row times the first number in this column, and then the second number in this row times the second number, okay? And then we're going to add it together. So once again, 5 times negative 1 plus 1 times 1. So 5 times negative 1 is negative 5. 1 times 1 is 1. So negative 5 plus 1, I believe, is negative 4. Now, this starts to get like, you start to do a lot of this in your head, and you might want to write this stuff down. You know what I'm saying? Like to this next one, if I do row 1 times column 2, and of course that final answer is going to go right here, because this is the row 1 column 2 spot. You might want to go off on the side and write down like 5 times 4 plus 1 times negative 2. You know what I mean? Like, don't feel bad about writing all this out off to the side. You know what I mean? So again, first number 5 times first number 4 plus second number times second number. So again, like that's 20, and then that's a minus 2. So that's 18. Okay? Now let me pause for a second to point out that if we're doing rows times columns, like the rows of this matrix times the columns of this matrix, that means like there's got to be the same number of elements in these rows as there are in the columns. Like there's 2 here, there's got to be 2 in the column. But here's a nice way to remember that. When you line up A and B, like the orders, like 2 by 2, 2 by 2, because we want to do matrix A times matrix B, if the inside dimensions match, that means we can do this. So we're doing a 2 by 2 multiplied with a 2 by 2. If the inner dimensions, we'll call them, match, we can actually do the multiplication. If these two numbers didn't match, we wouldn't even be able to do it. Okay? And another fun fact is that the outer dimensions, that's going to be the shape of your final answer. So it looks like our final answer is also going to be a 2 by 2. All right. So anyway, but let's finish this off. So now we got to do row 2 times column 1 and then column 2. So here we go. 2 times negative 1, that's negative 2. And then 0 times 1, well, that's just 0, so negative 2. And now we got to do this row times this column. So 2 times 4 is 8. 0, that's another 0. So 2 times 4, so that was 8. And so right here, this is my final answer. Okay? Now, if we were, I just want to make a quick comment before we do like another example. If I was going to do matrix B times matrix A, do you think we'd get the same answer? Do you think A times B, is equivalent to B times A? Do you think they're the same? The answer is no. They are not. I mean, they're probably not. I guess they could be, but I'm sure like 99, like almost 100% of the time, they're not the same. Okay, like right here in this example, I would not get the same answer if you put this matrix over here on the left, and now you do these rows times these columns. You're just not going to get the same answers. So, you know, it definitely matters which matrix is on the left and which matrix is on the right. So again, doing this problem is different than doing this problem. Okay? So here we go. Let's do one more example. And let's make this a 2 by 3. And let's make this a 3 by, I don't know, 3 by 4. It's a big matrix. So this would be 2 rows by 3 columns. So let's do 1, negative 1, 2. Let's try to keep this simple. 3, 0, negative 2. So this is matrix A, a 2 by 3. And let's say matrix B is 3 rows by 4 columns. 1, 4, negative 1, it's 4 columns. 0, let's throw in a 5, a 2, some more columns. How about a negative 1? How about a negative 2? How about a 3? And then another 0. And how about another 2? And then how about another 1? So we have a 2 by 3. So if I wanted to do A, B, okay, first of all, A times B, so it's a 2 by 3 times a 3 by 4. Since these inner dimensions match, we can do this. So yes, you can multiply a 2 by 3 matrix times a 3 by 4 matrix. They don't have to have the same order. It's just that these inner dimensions have to match. And like I also said, these outer dimensions, a 2 by 4, that's what the final shape is going to be. Like when I multiply these two matrices together, I'm going to end up with a 2 by 4 matrix. So here we go. Here again, here's how this works. It's the rows of this matrix times the columns of this matrix. So do you see now how it's, so you said like there's 3 numbers in this row, 3 numbers in this column. So that's why we can do this. So here we go. Ready? 1 times 1, and then plus negative 1 times 4, and then 2 times negative 1. Okay, and then you're going to add all those together. So negative 4 plus 1 is negative 3. So this gets me a negative 5 in that spot. So it was like row 1, column 1. So that number goes in the row 1, column 1 spot. And let's keep this going. Now we got to do, this is going to be row 1, column 2. So row 1, column 2. 1 times 0 is 0. So 0, negative 1. So that's negative 5. 2 times 2 is 4. So negative 5 plus 4, that should be negative 1. I just did that in my head. Okay. Now we got to do row 1 times column 3 for this spot. So 1 times negative 1, that's negative 1. Negative 1 times negative 2 is 2. 2 times 3 is 6. So again, like, this really challenges your mental math. You might want to jot down scratch work or something. So I think that ends up being negative 7. And then we got to do row 1 times column 4 to get this spot. Row 1, column 4. So 1 times 0 is 0. Negative 1 times 2 is negative 2. 2 times 1 is 2. So 2 times 1 is 2. So we got negative 2 plus 2. So 0. And then now we just got to do row 2 times all of those columns. I would recommend you please try this on your own. If you haven't been doing this independently up until now, you should pause the video and try these last 4 numbers on your own, okay? And then unpause. But here I go. So 3 times 1 is 3. That's a 0. 2. So that should be a 5, I believe. And then we got to do this row times the second column. So that's 0. That's another 0. And then negative 4, I believe. And then that row times column 3. I'm going to get like both hands involved here. So negative 3. That's a 0. I like having a 0 there. So negative 3. And then negative 6. Negative 3. And then negative 6. Should be a negative 9. And now we got to do row 3 times column 4. So row 3, column 4. Row 3 times column 4. So 3 times 0 is 0. 0 times 2 is 0. And then negative 2 times 1 is negative 2. So I believe that is the answer. So once again, if these inner dimensions match, we can do it. And the final answer is going to be a 2 by 4. Now, if I wanted to do matrix B times matrix A, that would be a 3 by 4 times a 2 by 3. So if we attempted to do that, we would see that these inner dimensions do not match. And therefore, this is not possible. You couldn't actually do B times A. So you can do A times B, but you cannot do B times A. So I believe that does it for this lesson. So good luck on the assignment. Let me know if you need any help.